Hello everyone. So let's continue our analysis of three-phase systems. And as I mentioned in my last video, there are four different combinations. So star using star and delta connections. So let's do the first of that. So star star system or star star circuit. Let's call it. What I mean by this is the source is star connected and load is also star connected. So let's write three-phase source of phase voltages 100 0 degrees, 100 minus 120 degrees, and 100 angle minus 240 degrees. So these are the RMS phase voltages, and a three phase load of impedance in each phase. That is, let's take 2 plus J 7 ohms. So 2 ohms of resistance and 7 ohms of inductive reactance is there in this one. And then the source is star, that is this symbol, and load is delta, it is this symbol. And what we want to do in this here is determine or just say find all phase and line voltages and currents.
It's 9 o'clock.
Voltages and currents. So this is the question. Okay, so let's start solving this question. I'll begin by drawing the circuit diagram. So three-phase source and star connected. So this is first phase, this is second phase, and this is third phase. So this is VA, this is VB, this is VC, and you all know this is plus minus, minus plus here, and minus and plus here. And these terminals are labeled A, B, and C. Now VA value is, we already know that, so let's write that phase voltages. So VA, VB, VC are nothing but 100 0 degrees, 100 minus 120 degrees, and 100 volts minus 240 degrees. So these are RMS voltages. This is given to us. So this is given. Now, coming back to the load side, what we have? There is an impedance, and there is another impedance, and there is another impedance. Three impedance values. So I am using this box symbol to represent the load. And this is impedance. The impedance value is also given 2 plus J7. So this is in ohms. And this is same. So ZA, this is ZB and ZC. So instead of ABC, let me call Z for all. Now since this is balanced, there won't be any neutral wire needed. And even if it is there, since in a balanced circuit, the neutral current will be 0. Let's mark the line quantities. So these are the phase voltages. So let's mark the line quantities. So this is, let me use a different color. This is VAB, voltage of A with reference to B. And then this is VBC, voltage of B with reference to C. And overall this is VCA, voltage of C with reference to A. So that's why we put plus here and minus here. Already we have learnt in previous videos that how do you convert. So what is VAB? So not the equal to sign. So if I multiply this with square root of 3 with angle of 30 degrees, then I will be getting the line voltages, that is VAB, VBC and then VCA. So that would be, I can right away do this. So root 3 is 1.732 into 100 will be 173.2. So I'll just take 173 as the magnitude. Of course, we can do this in MATLAB calculation also, but then this is very much straightforward. So minus 120 plus 30 will be minus 90 degrees, and then minus 240 plus 30 will be minus 210 degrees. So this is done. So I have this as line voltages. So this is what is line voltages. Now, if this is a line voltage applied, what are the phase voltages at the load? So again there will be VA here, and again there will be VB here with reference to this VB. Again there will be VC here. So just by going by same logic, so VA, VB, so the sign also would be like this will be high voltage, this will be low voltage, this will be at a higher voltage, this will be a lower voltage. So VAB in turn is equal to again VA minus VB, I guess. Yeah, so that anyway we have already done here. So the same VA will be coming here because everything is a symmetrical one. So this VA is exactly equal to this VA. So this phase of the load will see the same A phase voltage. So simple Ohm's law, I can find the phase currents of the load. So let's mark the phase currents of the load. So this time the current will be in this direction. So this is IA and this is IB and this is IC. So why am I taking the currents going into the load is because this is a load and this is the source. So this is a natural direction of current I am assuming. So how do I find IA, IB and IC? Simply V phase by Z phase. So V by Z will be the current IA. So and similarly VA by IB will be VB by Z and VC by Z. So let's do that calculation here. So this above IA, IB, IC, these are load phase currents. Load phase currents if I want to find. So that is nothing but VA, VB, VC all divided by Z. So each element I have to divide by Z. So that's why I've just given like this. So that is 100 angle 0 degrees divided by 2 plus J7 and so on. 100 angle minus 120 degrees divided by 2 plus J7 and so on. So let me not write all this here. Let's do it from calculation from MATLAB interface. So let me switch over to MATLAB interface. So what I want to define now is VA, that is 100, VB, that is 100, EXP, I into minus 120 degrees, but then I want to define it as radians. So in fact I already know the radians, so that is 2 into pi by 3, minus 2 pi by 3. So this is VB and then VC will be 4 pi by 3. So I have defined now VA, VB and VC. So now once I have this, so VABC, I will define it as a matrix. So VA, VB, VC. So this is my three voltages expressed in rectangular form. Now my Z is nothing but 2 plus I7. I'm sorry, I into 7. So Z is also defined. So VABC divided by Z. So here it will just multiply all the elements, and what I am getting now is all the currents. So let me call this as IABC equal to this. So these are the load currents at the phase side. So I want to know the magnitude of this. So just say ABS of IABC. So this will give me the absolute values 13.736. So let me write it down. So IAIBIC is 13.736, 13.736 and 13.736. But what about the angle? So let's look at the angles. So ANG angle and IABC. And this will be in radians, so I want to convert into degrees. So I'm just multiplying by 180 and dividing by pi. So these are the angles, minus 74 degrees. So I'll just round it off to minus 74, 166 and 46. So this is minus 74, 166 degrees and 46 degrees. So here I got the currents in this fashion. So it also helps to know what is the angle of impedance Z. So let me do that here. So absolute value of impedance 7.238 and then angle of impedance. This I will multiply into 180 and divide by pi. 74 degrees. So this is actually my impedance is 2 plus J7, which is nothing but 7.28 and at an angle of 74 degrees. So now naturally you see the IA current is lagging the main current. So the VA voltage is 0 degrees. So this is lagging by 74 degrees. Now one thing here, it is a little bit confusing. So here VB angle is minus 120 degrees, but here this is plus 166 degrees. So it might give you an impression that the IB current is leading the VB voltage, but it's not actually true. This is because this is measured clockwise direction and this angle is measured anti-clockwise direction. So let me give a pictorial representation. So this is VB and this angle is 120 degrees because VB was how much? So this is 100 angle minus 120 degrees. What about what we just calculated, IB? So IB is 13.736, angle is 166. So this is almost 180 degrees. So 166 degrees will be something like 14 degrees less than that. So somewhere like this. So this one is IB. So this value is 13.73 and the angle is 166 degrees. So this is 166 degrees. So therefore this angle is 14 degrees and this angle is 60 degrees. So 14 plus 60 degrees is 74 degrees. And if I take VB as reference, IB is lagging VB by 74 degrees. So that is confirming, because that's why I wanted to know the angle of the impedance. Because impedance angle is 74 degrees, the current will be lagging the respective phase voltages by 74 degrees. Anyway, this is just for confirmation. If you also want to see the relation between IC and VC, that also can be done. So let's very quickly do that. So this is phasor diagram to show IB and VB. So same thing I want to repeat for IC and VC. So what is VC? C phase voltage. So this is 0 degrees and this is 120 and minus 120 or plus 120. Sorry, minus 240 or plus 120. So VC is nothing but 100 angle minus 240 degrees. That means this entire angle is 240 degrees. So if I'm starting from 0, if I go clockwise, it will be counted as a minus angle. Now, what is the angle of the current IC? So if I go up, here you can see IC current angle is 46 degrees. So it is like this. So this is like exactly half, because this is 90 degrees, so almost half. So this is, so this angle is 46 degrees. So therefore this angle will be how much? Total will be 90. 90 minus 46, or you can do another way to find the phase difference. So this total angle is 120. 120 minus 46 will be 74 degrees. So that is what we are interested in, to know the phase difference between VC and IC. So this is another vector diagram. I am not drawing for VA and IA, because that is just obvious, straightforward, because you see VA angle is 0 and this is minus 74. So therefore the IA current is clearly lagging VA by that. Okay, so far what I have calculated, so these are line voltages, these are phase currents of load, which are nothing but line currents, because the load is star connected. So whatever is the phase current is nothing but the line current, which is also nothing but the phase voltages of the source. Sorry, phase currents of the source. So let me explain it again. So I phase source equal to I line from because source and load are sharing the same line, so I'll just say I line, which is also equal to I phase of load. That is because this is a star connection, this is also star connection that is there, and the voltages also we have done. So what we have now, everything that is required, that is phase voltages of the source, line voltages, and then phase voltages of the load also. So these are phase voltages, source, and also load. That is because star connection. So just follow the network circuit and then you will be able to easily get what is going on here. So I hope you got some idea about this case. So in the next video, we'll try to take the another combination, that is, I'm sorry, here I mentioned delta, so I think this is all wrong. This should be star. So in the next case, I'll keep the source as star connected, but the load I'll keep it as delta connected, and then we'll try to see what it is. So before we wind up, just let me calculate the total power. So total power is nothing but root 3 VL IL cos phi. So root 3, what is line voltage? So if you go up, so the line voltage we have here is 173. So any magnitude of line voltage I can take it, 173. And what is the line current? Line current or phase current is exactly same. So that is 13.736. So 13.736. And then cos phi is the cos of the angle, 74 degrees. I should put minus sign here because the power factor is lagging. However, for cos it doesn't matter, plus or minus, the cos minus 74 is same as cos 74. But then we have to mention that the load is lagging. Anyway, so let's calculate the total power. So for this I'll use again my MATLAB interface. So square root of 3 multiplied by VL, that is 173, multiplied by IL, that is 13.736, and then cos of minus 74 degrees. But then cos requires radians, so I convert to radians by dividing by 180 and multiplying by pi. So 1134.5 watts of the total power, 1134.5 watts of the total power being consumed. So the same power, you can also calculate 3 into V phase into I phase into cos phi. So that is also will give you the same result. 3 voltage of phase is 100 volts and current is 13.736 and cos of minus 74 degrees. So you notice these two terms are same here. Now here the root 3 and this 1.732 into 100, so that you see is exactly same. So if you feed this into calculator, you will again get 1134.5. So you can use any of these two formulas depending on the values that are there to find the total power in the this one. So very quickly, let's also find the reactive power that is consumed. Reactive power consumed by load. Now, you can easily imagine, because the load is 2 plus J7, so this is magnitude wise, this is more than this, so there will be more reactive power consumed by the load. So let's do that. So Q is root 3 VL IL sin phi. So exactly same thing, just sign will be different. So let me calculate that. Just I replace cos with sin. So minus 3956. So minus 3956.5. So again, don't worry about the minus sign, because we know that Q is a reactive power. So I'll just, so I'll say 3956.5 wars of reactive power is consumed. I think enough of our study on this. So let's do the next video, and then we'll calculate the another combination star and delta. Thank you. Oh, this is the 10th page.